Hello, this is our presentation for Refrigeration Lab. We are Team 1 from Section 7 of ME 4056 Systems Lab. The problem that our team faces is that our client, Machine Chillers, has developed a new vortex tube that uses air as the working fluid. They would like for our team to model the system and determine its capabilities, characteristics, and the associated uncertainty. The analysis of this system will be performed over the course of 2 weeks, with the first week focusing on the steady state response and the second week focusing on the transient response as a function of time. The new machine chiller's refrigeration system is shown here in the diagram on the left. There are four 12-volt batteries wired in series connected to a motor controller, which controls the motor RPM through a changing input voltage. The motor turns a crankshaft of a piston inside of a compressor, which uses a series of one-way valves to raise the pressure and temperature. The compressed air passes through a heat exchanger, which reduces the temperature back to ambient before it's pumped into an accumulator tank, which acts as a reservoir to hold compressed air and remove any cyclical pressure variation due to the compressor and release it at a constant pressure to the vortex tube. The vortex tube spins the compressed air at approximately 1 million RPM, with heat energy transferring from the inner vortex to the outer vortex. The hot air is vented back to the atmosphere, while the cold air is directed through the aluminum block load before being released to the atmosphere. There are 6 different locations where temperature is recorded using thermocouples, 4 locations where pressure is recorded with pressure transducers, and 2 locations with flow meters on the hot side of the vortex tube and after the cold air has passed through the aluminum block. All sensors are connected to a myRIO Elvis3 board, which collects data in a custom LabVIEW VI. So the procedure for the first week of lab was to collect data at steady state. First, we determined gauge offsets by collecting the data with the input voltage to the compressor at 0 volts, such that there was no flow through the system. Then the voltage was increased to 0.5 volts, and the system was allowed ample time to reach steady state. We found this to be approximately 2,500 samples, or close to 21 minutes. Once the system had reached steady state, 400 samples were collected of the 6 individual temperatures, 4 pressures, and the flow at 2 exit ports with the flow to the atmosphere. So once the data was processed into a spreadsheet, the input voltage was increased by a half volt and the process was repeated. In total, this procedure was performed for 0.5, 1, 1.5, 2, and 2.5 compressor input voltages, and the associated relationships between voltage, pressure, and steady state temperature could then be determined for our system.
First key system to look at for the following refrigeration cycle is the heat exchanger accumulator tank subsystem. The role of this subsystem is to transform high pressure, high temperature air from compressor to high pressure room temperature air output. Performance of the following system was first evaluated by comparing the output temperature, which should be theoretically close to the room temperature. The results show that the subsystem fails to produce output temperatures that is close to room temperature at higher voltage inputs. This adds liability to the entire refrigeration system performance at higher voltage inputs because the following subsystem is failing to produce intended output temperature at higher voltage inputs. Further analysis was taken on the relationship between the input voltage and the pressure output of the system. The relationship between the input voltage and the pressure output showed nonlinear relationship. The changes in pressure was higher in voltage changes at lower voltage settings, and the changes of pressure started to decrease in voltage changes at higher voltage settings.
The temperature at each stage of the air from the air tank is given in the table. The things to note in this table are the load temperature and the cold air temperature. We assume that the insulated load would reach a steady state and there will be no heat transfer between the cold air and the load. However, because the temperature of the load and the cold air is different, there may be heat transfer between the load and the air. As the air pressure at stage 3 increases, the cold air's temperature decreases. However, since they do not show a linear relationship, the relationship between them can be expressed as a nonlinear exponential function. As the air pressure at stage 3 increases, the hot air's temperature increases. And since they show a linear relationship, we did a linear regression using York fit. As the air pressure at stage 3 increases, the cold air's mass flow increases. Since they show a linear relationship, we apply the linear regression using York fit. As the air pressure at stage 3 increases, the hot air's mass flow increases. However, since they do not show a linear relationship, the relationship between them can be expressed as a nonlinear exponential function.
Final area to further analyze is the energy balance at the load. At steady state, it was assumed that energy leaving the load is zero, which means that the total energy transferred into the cold air should equal the energy entering the system from the environment. Total energy transferred into cold air was calculated using measured mass flow rate, measured temperature, and given specific heat of air. And using the following energy balance equation, thermal conductivity for styrofoam and thermal resistance for the styrofoam was experimentally derived. It was compared with the given theoretical conductivity and theoretically calculated resistance. The results show that the resistance and conductivity are not independent of the test pressure. This could be due to several poor assumptions for the styrofoam itself. The covering of the styrofoam was not perfect and had limited insulation at certain areas of the load. Also, the thickness was assumed to be the same across all surfaces when imperfect surface conditions existed for the given styrofoam cover.
The calculated theoretical and experimental values for the ambient heat transfer rate are shown in this table based on the calculations from slide 10. And these calculations were based on the theoretical and experimental values for insulation resistance and thermal conductivity. The discrepancy for each input voltage was found by taking the difference in the theoretical and experimental values. And the uncertainty based on the sensors was found for each voltage input. The discrepancy is outside of the bounds set by the uncertainties for voltage inputs ranging from 0.5 to 1.5 voltage. And based on this, we can conclude that the modeling discrepancy is likely due to poor modeling as opposed to the sensor inaccuracy for this voltage range. We can also conclude that the sensors likely failed to distinguish modeling discrepancy and uncertainty during measurements with an input voltage of 2 volts or higher. Testing in week 2 will involve modeling transient cooling of the aluminum block by the compressor and the building air as the load temperature moves from ambient temperature to steady state. 2 tests will be run, the first where the compressor at a pressure gauge of 40 psi will cool the load, and the other where the building air will cool it. The voltage-pressure relationship defined from the data in week 1 is necessary to determine what input voltage corresponds to the P3 pressure associated with the reading of 40 psi. Using this input voltage, the temperatures of the load and at states 1, 3, and 4, along with the pressures, will be collected for these tests. And once the data is collected, a transient analysis will be done using the lumped capacitance method, in which the assumption is made that the entire load is at the same temperature at a given time. The total energy change throughout the cooling is found by integrating the energy change rate equation across the total time, which is based on the rate of change of the temperature of the load. In this equation, the delta T term is the change in temperature of the aluminum block from start to end of each test. Then the Q ambient and Q air will also be calculated using the same equations found in slide 10, and the insulation resistance calculated from week 1 is necessary to find the ambient heat transfer. This time though, the load temperature and T5 won't be constant, so these heat transfers must be found through numerical integration by taking the sum of every heat transfer rate across the start and end time. And then lastly, Q discrepancy will be found and the system modeling capabilities will be judged again, and the low temperature values will be compared for the transient and steady state tests. And then the uncertainty analysis will also be done based on the equation shown, which will include the calculated discrepancy.